What about the Arctic? Will an ozone hole form there as well? Key to understanding the chlorine chemistry in the polar stratosphere is the measurement of polar stratospheric clouds, chlorine monoxide, and the reservoir gas, chlorine nitrate. Polar stratospheric clouds are seen by the improved stratospheric and mesospheric sounder, ISAMs, and chlorine nitrate is measured by the cryogen limb array echelon spectrometer, or CLAES. Both ISAMs and CLAES make measurements by looking at infrared emission from cloud particles and trace gases. The CLAES, MLS, and ISAMs measurements together show us that the polar stratospheric clouds which form in the cold Arctic stratosphere have converted most of the chlorine nitrate into the radical chlorine monoxide. In 1992, UARS measurements showed conclusively that an Arctic ozone hole is beginning to form. CLAES also measures the infrared emission from CFCs in the stratosphere. CLAES measurements show beyond a doubt that significant amounts of CFCs reach the stratosphere. The decrease in CFC concentration at higher altitudes in the stratosphere indicates that CFC molecules are being broken up by ultraviolet radiation. Are CFC amounts changing in the stratosphere? The answer to this question comes from the third instrument measuring the chlorine chemistry in the stratosphere, the Halogen Occultation Experiment, or HALO. HALO was designed to carefully monitor hydrogen fluoride and hydrogen chloride, byproducts of CFC destruction in the stratosphere. HALO operates by observing the absorption of infrared radiation by these molecules against the rising and setting sun. When UARS was first launched, measurements by HALO showed that CFC byproducts were still increasing in the stratosphere. But the newest HALO measurements now show that CFC byproducts are no longer increasing. UARS has shown that the stratosphere is starting to respond to the international ban on CFC manufacturing. By measuring water vapor amounts, HALO measurements have also shown us that it takes about 5 years for CFCs to reach the upper stratosphere. Tropical water vapor changes slowly with seasonal cycles. These changes, shown here as thick bands, were found to slowly ascend. These measurements tell us how fast the CFCs and other pollutants rise into the stratosphere. UARS has provided an unprecedented new picture of the upper atmosphere chemistry. The stratosphere is a dynamic region, and to understand ozone, we must know how the upper atmospheric winds transport trace gases. Two instruments on UARS directly measure these winds. The Wind Imaging Interferometer, WINDY, measures the winds in the mesosphere using airglow. The high-resolution Doppler interferometer, HARDY, measures winds in both the stratosphere and mesosphere. The tropical winds in the stratosphere undergo a slow 2-year variation called the quasi-biennial oscillation. This oscillation controls mixing throughout the stratosphere, and HARDY has given us much more detail on wind changes associated with this oscillation. To understand the solar effects on the ozone layer, UARS was equipped with 3 instruments to measure the sun. The first, the Active Cavity Radiometer Irradiance Monitor, or ACRIM, measures the total energy output from the sun. The other 2 instruments, the Solar Ultraviolet Spectral Irradiance Monitor, SUSIM, and the Solar Stellar Irradiance Comparison Experiment, SOLSTICE, measure the sun's ultraviolet radiation. It is important to know the exact solar ultraviolet intensity because the amount of ultraviolet light changes with the 11-year sunspot cycle, and this causes a change in the amount of ozone. Since ultraviolet radiation is screened by the ozone layer, solar measurements must be made from space. SUSIM and SOLSTICE have provided the first comprehensive direct measure of changes in the solar ultraviolet spectrum over the solar cycle. UARS also measures the flux of energetic particles from space using the Particle Environment Monitor, PEM. These high-energy particles cause ozone depletion at high altitudes by producing nitrogen and hydrogen radicals. All of the data from the UARS instruments are publicly available from NASA's Distributed Active Archive Center. More information can be found on our webpage. By all measures, the UARS mission has been a tremendous success. However, there are new threats to the ozone layer. NASA is ready. The technology developed for UARS is now being refined for the next generation of chemistry instruments to be launched on EOS Chem.